In this final video for Chapter 20, we will go over acid anhydrides, esters, amides, nitriles, and give a brief summary. Acid anhydrides can be prepared from carboxylic acids using sodium hydroxide as well as an acid chloride. Now the way this mechanism is going to work is we're going to start with the carboxylic acid, and when it's treated with sodium hydroxide, which is a strong base, we're going to remove the acidic proton. And we will form our carboxylate ion. Now this carboxylate ion is capable of acting as a nucleophile. So when it comes in contact with our acid chloride, which I'll go ahead and put in red, we can have the electrons come over, attack the carbonyl carbon, kicking the electrons up onto oxygen. Now, as we've seen in the previous mechanisms, we're going to reform the carbonyl. The electrons will come down and kick off the chlorine. And that is how we form our acid anhydride. So the acid anhydrides are very similar in reactivity to the acid chlorides, but instead of having the chlorine act as the leaving group, we're going to have this entire group here act as a good leaving group. So we'll see on the next slide that acid anhydrides act very similar to the acid chlorides. So you'll notice that most of these reactions for the acid anhydrides are nearly identical to the reactions for the acid chlorides. So again, even though the acid anhydrides are slightly less reactive than the acid chlorides, they perform the exact same reactions. So again, you can kind of break these down into categories. Starting with an acid anhydride, you can turn it into either an ester or carboxylic acid using alcohols or water. Now the difference between these is we do not need to have pyridine in this solution because we won't generate HCl as a byproduct. We can also react an acid anhydride with amines to turn them into amides. We can reduce it into an alcohol. We can also reduce it into an aldehyde using our less reactive version of LAH. We can react them with Grignard reagents to form alcohols, and also Gilman reagents to form ketones. So you do not need to memorize a whole new set of reactions for acid anhydrides. They're exactly the same and exact same mechanisms as the ones for acid chlorides. The next derivative we'll talk about are esters. Esters are when you have a carbonyl connected to an oxygen, which is connected to an R group. So again, these are derivatives of carboxylic acids. Now to name esters, we're going to break the ester into two components. We will have the carbonyl and oxygen plus whatever R group is attached to it, as well as the R group attached to the oxygen. This is going to be treated as a substituent. And this component comes from a carboxylic acid. So let's consider the name of this in its carboxylic acid form. We have a 2-carbon chain, so it would have the name ethanoic acid. So what we're going to do is we're going to modify this name to become ethanoate. Okay, so in an ester, we take away the IC acid and we replace it with ate. Now this is going to be the parent chain name. Now as usual with naming, we're going to start with the name of the substituent, which is a propyl group. So the full name for this molecule is propyl ethanoate. Now you might recognize this name also can be acetic acid, and that is the common name. So to give a more common name for this molecule, again, we're going to take that IC acid and convert it into 8. So we get acetate. So the common name for this molecule can be propyl acetate. And either one is appropriate. So now let's try it with our second example. We have this component of the carboxylic acid. We also have a cyclopentyl group. Now normally this name would be propanoic acid. So what we're going to do is when it's converted to an ester, we're going to take the IC acid and replace it with 8. So we get propanoate. So our full name for this molecule is cyclopentyl propanoate. Now, esters are most often prepared using a reaction called the Fischer esterification. We're actually going to be using this reaction in lab. This reaction in general takes a carboxylic acid plus an alcohol with an acid catalyst, and the reaction turns into an ester and water. So let's go ahead and take a look at an example of the mechanism for the Fischer esterification. Now this is one of the few mechanisms that involves an acid catalyst. So in these mechanisms, the first step is we're going to protonate the oxygen of the carbonyl. Next, we will have an attack by the nucleophile, and we'll go ahead and use ethanol as our alcohol. It'll come in, attack the carbonyl carbon, and kick the electrons up onto oxygen. Next, we're going to remove the extra H, and ethanol will act as a weak base to remove it and give the electrons back to the oxygen. Next, one of the two OH groups is going to be protonated. So the ethanol that just removed the extra H is now positively charged, so it's going to act as a proton source. And what we're doing is we're turning one of these hydroxyl groups into a good leaving group. So our next step is the other OH group that has not been protonated is going to donate its electrons to form a double bond and kick off the leaving group in the form of water. And in our last step, another ethanol can come in, act as a weak base, get rid of the extra H, and we form our ester. So esters are a little less reactive than the acid chlorides and acid anhydrides, so it's going to undergo fewer reactions. I'm going to go over about 3 of the reactions that esters can do. The first is saponification, and this is also known as base catalyzed hydrolysis. This is an important reaction because it's how soap is made, and we will actually be performing this reaction towards the end of the semester. In saponification, you take an ester and treat it with sodium hydroxide and heat, and what you end up forming is a carboxylate salt. Now this is actually soap. Now we can either leave it in this soap form, or if we wanted to take this molecule and treat it with hydronium or an acidic wash, we can convert the ester back into a carboxylic acid. So if you stop at this point, you'll actually have soap. If you continue on, you can convert it to a carboxylic acid. Next, we have acid-catalyzed hydrolysis. With acid-catalyzed hydrolysis, you simply take an ester and treat it with hydronium to convert it into a carboxylic acid. This is a very simple process, and as a result, it's a simple way to use an ester as a protecting group for a carboxylic acid. So if you have a carboxylic acid in your molecule, it can get in the way because of that acidic proton. But what chemists often do is they will protect the carboxylic acid in the form of an ester, and they'll return it back to a carboxylic acid at the end of the entire synthetic process. So this type of acid-catalyzed hydrolysis is used a lot in peptide synthesis. Lastly, we can reduce esters to aldehydes, similar to the type of reaction we saw with the acid chloride and the acid anhydrides. Now in this process, you start with an ester and you treat it with a reagent called DIBA. And DIBA stands for diisobutyl aluminum hydride. So that's where those initials come from. Now this is very similar to the LiAlOR3H. So it's a less reactive version of LAH. Now esters are very tricky because they're not as reactive as acid chlorides and acid anhydrides. This is not a simple process to reduce it. However, chemists have found that DIBA is the best reagent. Amides can be prepared from acid chlorides reacting with amines. Now we can also use, in place of acid chlorides, we can use acid anhydrides or even esters. So several of the carboxylic acid derivatives are capable of converting into amides. Now we can either use ammonia, you can also use primary amines, or secondary amines. And they will all form the amide functional group. Now amides are the least reactive of the derivatives that we've learned about so far. Now, amides undergo hydrolysis, and they can do either acid or base catalyzed hydrolysis. So we can either use H3O plus or a combination of sodium hydroxide and heat as well as H3O plus. So these are the same types of reagents that we saw with the ester hydrolysis. But either way, we take an amide and we can convert it back into a carboxylic acid. Now amides can also be reduced to amines using excess LAH. Now this is a very interesting reaction because typically LAH forms alcohols from carbonyls, but in this case it's actually going to get rid of the carbonyl completely. Now the mechanism for this reaction is not entirely known, but we're guessing that from the point of forming the alcohol with the NH2, the NH2 actually kicks off the OH as a leaving group. And it's going to form an intermediate that is somewhat like an imine. Then that causes the aluminum hydride to react with the carbon of the double bond, similar to what we've seen in previous mechanisms. And that gives the electrons to the nitrogen. So this is just a proposed mechanism for reducing an amide all the way down to an amine. So next we're going to talk about nitriles. Now even though I didn't introduce nitriles at the beginning of this chapter, a nitrile is technically considered a carboxylic acid derivative. A nitrile is when you have an R group attached to a carbon that's triple bound to a nitrogen. Now, nitriles are the least reactive of all the carboxylic acid derivatives, so they're not as useful in synthesis as the other ones would be. So we'll go over two main ways to prepare nitriles. The first is with one of the reactions we've learned at the very beginning of organic chemistry, and that's just a basic SN2 reaction. So we'll start with an alkyl halide, and we want to use a primary or methyl alkyl halide, and we'll treat it with sodium cyanide. Now the cyanide ion has a negative charge and is a good nucleophile. So the cyanide will simply come in, attack the carbon containing the leaving group, kick off the leaving group, and form our product. So this is an SN2 mechanism. And it's important to note that this reaction also adds one carbon. So you have to be careful and count your carbons with these types of reactions. We can also create nitriles from amides by treating them with thionyl chloride. I'm not going to go through the mechanism for this, but this type of transformation will also give a nitrile. Now, nitriles participate in pretty much the same types of reactions as all of the other derivatives. So we have hydrolysis, the acid or base catalyzed with either H3O+ or sodium hydroxide followed by H3O+. And again, that's going to convert our derivative back into a carboxylic acid. Similar to amides, we can also reduce nitriles to amines using excess LAH and water. And then what's unique to nitriles is they can actually react with Grignards to form ketones. Again, we're not going to go over the mechanism, but it's important to highlight that there's other ways to create ketones other than the ways that we've learned so far. So again, taking a nitrile, treating it with a Grignard, and we end up forming a ketone. So in this chapter, we've gone over all of the different types of carboxylic acid derivatives. In the summary, I want you to see how they are all connected with one another. So starting with carboxylic acids, we know that we can turn them into acid chlorides using thionyl chloride. Now from an acid chloride, we can actually create an acid anhydride using a combination of NaOH and a carboxylic acid. Now we can turn an acid anhydride into an ester using an alcohol. We can turn an ester into an amide using an amine. And finally, we can turn an amide into a nitrile using thionyl chloride. Then, to link it all together, we can turn a nitrile back into a carboxylic acid using acid or base catalyzed hydrolysis. Now there are many more connections with all of these derivatives. At any point, we can turn all of them back into a carboxylic acid. We can also turn an acid chloride into an ester. But you'll see that we can easily turn all of these into each other using various reagents.